Mm. Okay. We had a few slides left on the previous lecture, but as I said earlier, that sometimes the material which is important for the course will not necessarily be covered at the lectures because it's easy. So the next 7 slides or so are fairly easy. So in the interest of getting some more time to discuss things which I know are a little bit more difficult, we will skip these. But typically, but I encourage you to look through these and try to understand what they are saying. We will obviously return to this later on also. But there is a physical layer at the bottom of the protocol stack. It's responsible for transmitting bits. It's very different from depending on the type of media we have, if it's fiber optic cables or radio. Data link layer is to organize transmission of packets of bits, and it needs to perform some services in order to do this. Framing, flow control, error control, medium access, addressing, activation, maintenance, and deactivation of links. Okay, so this goes quickly now through these slides. Network layer, responsible for transfer of segments over multiple links. Okay, and possibly also multiple networks. So many different things it needs to do, figure out routes and so forth. Transport layer, it's the first end-to-end protocol. So it's responsible for transmitting information from the endpoints in 2 different ways, typically. Many things that needs to be done. We'll talk more about this later. Layer 5, 6, and 7 are typically all bunched into one protocol called the application layer. And it provides services to application programs that are very handy to it. DNS, FTP, remote login, things like that. Email. Okay, so that's it for that lecture. And let's move on to the next lecture. I jumped into the middle of it. Okay, so here, now we will talk about internets and what they are, and a little bit on the TCP/IP protocol architecture, and then move into the physical layer, some details about the physical layer. Terminology, network, connection of nodes and links. We know this. Nodes are either hosts or routers. Hosts are end devices running some software that support users. Routers is in between, transferring data from point A to point B. Link is a physical medium that connects nodes. An application or a program is something that uses the network, for instance, Spotify. A layer is a set of related communication functions that provide services to the layer above it, using services from the layer below it. Service is either connection-oriented or connection-less. Connection-oriented means that we create a logical connection between the endpoints before we start to transmit. A protocol, a layer can consist of many protocols, but a protocol cannot span many layers. An entity at layer N is a piece of software or hardware which is executing the layer N protocol. Entities at different nodes are called peer processes because they are peers, equals, right, in the hierarchy. They communicate by exchanging PDUs, protocol data units. Layers at the same node communicate up and down, and they do that by exchanging service data units. Okay, so the protocol data unit I have at this layer, when I push it down, then that's the service data unit for the layer below me. And obviously, the protocol data unit for the layer above it becomes my service data unit when it's pushed through the roof. Okay. SDU service data units are encapsulated into PDUs. So PDU typically is a header, an SDU service data unit, and maybe a trailer. We can segment SDUs, which means that if they are too big, we can split them apart and send them individually and reassemble them at the receiver. A layer may put several PDUs in a single several service data units in a single protocol data unit, and this is called blocking or aggregation. So that's if there are two small pieces, I can put them into a bigger packet. A layer can serve several entities above, and this is called multiplexing. A layer can use several entities below, and this is called splitting. Okay. So from the perspective of me, multiplexing means that I can serve many users above me. Splitting means that I use several of the services below me. Okay. Application layer specific names for PDUs are sometimes used. So at the application layer, these are called messages, transport, segment, network, packet, link, frame. We will call them packets almost always. Packet or frame. Okay. And here's the OSI model, 7 layers, while the top 3 ones are typically bunched into one layer, called the application layer. Numbering 1, 2, 3, 4, 7. Okay. And here are the responsibilities for the different layers. Provide services for application program, end-to-end transfer of messages, transfer of packets over several links, transfer of frames over a single link, transfer of bits over a physical channel. That's the responsibility of the different layers. Okay. Questions? So this was a super quick review of what we did previously today. No? Okay. Internetworking then. Okay, so there are several network technologies like Ethernet, Wi-Fi, cellular, LTE, 3G, you name it, right? Many different types of networks. So sometimes a host is connected to one network but would like to communicate with a host on another network. That happens quite often. So a process of building a super network, that is a network of networks, that is called an internet. And it operates over several of these network technologies, possibly several networks, possibly of different technologies. So the biggest internet in use is the internet with a big I. Okay. So what is done here is that we connect the different nets with special nodes called gateways. These are special routers, and they need, for instance, if network 1 and 2 are different technologies, then this router this gateway needs to be able to talk. These two has to have hardware and software to support both network technologies. Okay. Inside each net there might be routers, but these are working with the same type of network technology, so there are typically simpler devices. Okay. So gateways are these special devices that could connect different networks together. And then if we add the network, we can just put in gateways there, and then we increase the size of the interconnected networks. And the whole thing then becomes an internetwork. Okay. So this is super powerful, right? It's very modular, and as long as we can make this work, it's awesome, right? So as soon as somebody puts up a Wi-Fi network with the right gateways, we enlarge the internet, right? And likewise, if somebody tears down a network, a Wi-Fi network, connectivity might be lost to this host if it's the only connection it has, but it does not affect the rest of the network. Questions? No. Okay, so now we run into, so this has been, the internet has evolved organically over the years, I would say, without a master plan of what the end result should be. It just adapted to the needs of the time, and it started as a research network, maybe with some military applications in mind, and then it then evolved into the super useful thing that we call the internet today. So nobody in the 60s had this big plan that the internet should look like what it does today. So both the technology, the network technologies here, and the protocols have evolved, right? So they are not so nicely structured as the layers are in the OSI model. So the OSI model is a theoretical model where people sat together in committees and thought about, if we would build the network, it would look like this. At the same time, the network was built without any specific master plan, right? So therefore, it's a little bit messy in reality. So the nice ideas here are somehow reflected here, but not perfectly in all aspects. And one thing which is annoying is that, okay, so internet model, what is that? Well, it's a 5-layer model or a 4-layer model, depending on where you read about it. So that's just an indication of it, that it's not very structured. So in this course, we will think of it as a 4-layer model. Well, mostly at least. Okay, so at the bottom here, we have the network interface layer, and then there is the internet layer and the transport layer and the application layer. And if one would translate the OSI layers into this, then essentially the network interface layer contains parts of 1 and 2, these two, and then parts of 3 here. The internet layer is a piece of 3 in the OSI layer, and the application layer is typically the same. So this internet layer here is called, or sometimes also called the IP layer. So IP, Internet Protocol, is what makes this internet tick, right? It creates the network of networks. So it should be able to work over different network technologies, right? And an IP packet transmits information over an internet. So it starts at an host A and should arrive at a host B, okay? And then it goes from host A to a router, to a router, to a router, etc., until it reaches the end destination. Okay, and these routers are these boxes here. They are connected to networks. So if there is a packet at node A that needs to reach node B, there is a transport layer at node A that would like to talk to a transport layer at node B. So what is happening here is that this data then goes down the protocol stack and then is transmitted on its way to this one. So it could be, for instance, like this. It goes down and then it goes over this and then it goes like that. Okay. It's maybe hard to see, but when it came over this network, it went into the network interface here, which does not understand anything about IP. So it has to go up to the IP layer here in order to get processed and then fed down on the other side to go over this network. So there is actually a vertical line here also, that we have a protocol stack to the left and a protocol stack to the right. But it goes up here and then across the internet layer and then down to typically possibly another network interface here, depending on the network technology in the two networks here. So again, if we have another packet, it goes like this. It took another route through the network here, and that's fine too. The transport layer doesn't care as long as the data arrives. So the IP layer here is trying to use the network as efficiently as possible by providing connectivity, end-to-end connectivity for the transport layer. Questions? Okay. Yes?
Does that require the internet layers to understand the most efficient path through the network?
Exactly. So one of the things, and we haven't talked about this, is that the internet layer entities, this one talks to this one, and this one, and this one, to figure out the topology of the network, which is unknown, and figure out the best routes through it. And what makes it difficult is that this network is also dynamic. I mean, this gateway might crash. There might be a power outage in Brazil or something, right? What to do? Then one has to adapt. So this happens constantly, right? So it's almost like a living organism here. Okay, question?
We never know if it has actually arrived.
Will we? Okay, so the question is, will we know if data has arrived? Hold that question a little bit. But I can say that the internet layer has no idea. However, the transport layer keeps track of what it has transmitted and requests the transport layer here to acknowledge that it has received it. Okay. At least when it comes to TCP, it does that. So if this transport layer here sends some data and don't hear anything from the transport layer here, it assumes it's lost and then retransmits it. For TCP. For UDP, it doesn't. But for TCP, it does. So some transport layers are reliable and some are not. IP is unreliable, that's for sure. Okay, so if one looks at the protocol suite and the layers for TCP IP, on top we have these some familiar and some not so familiar protocols which are providing support to application software. HTTP, we talked about that. SMTP, do you know what that is? Email, yeah. Simple Mail Transport Protocol. DNS is to translate between internet names, you know, www.chalmers.sc and IP addresses. RTP is a real-time transport protocol, and there is loads of these protocols. All of them providing some useful service, some more useful than others maybe. Transport layers typically has two network protocols which are used by these. And these are, it's TCP and UDP, and TCP, yeah, we'll talk about that, the difference between that. If we go down one layer, we have IP. That's the only protocol here, which is directly used by TCP and UDP. And then at the bottom here, we have a big mess in the sense that there are many network technologies. Everything from your ADSL modem, if you still have one, or fiber modem. There's cellular, LTE, 3G, 2G, maybe even, not 1G is not part of this, 2G for sure. We have Wi-Fi, we have Ethernet, and many other things here. So the key to why this works is that there is a unifying entity here that's able to talk over all of these somehow, and therefore TCP and UDP can work efficiently without knowing the details about what's going on here. So that's the real power here. Of course, this IP layer is complicated, right? But it works pretty well, at least. So the service that IP is providing, okay, so it's the service it provides upwards. What is that? It's best effort, connectionless packet transfer. So let's do this in the back way. So it transmits packets, and it's connectionless, which means that it does not talk to the other side before it sends the packet. So it receives a packet and wham, it goes, right? No idea if somebody's listening. So it's not reliable. One can almost understand it's not reliable, but it does its best, okay? So best effort here, one could say, I mean, one can scrap that. Of course, it's a connectionless packet transfer, and it does the best it can, okay? So it's best effort, but no guarantees. No guarantees. So, but of course, we would like to have guarantees at a higher layer. So what TCP and UDP do is to refine the IP service to something which is more useful. And TCP is the workhorse for many things, like where you need reliable transmission. So it's a reliable transmission of data, and it's actually a reliable stream service, meaning that it accepts bytes. So somebody who's using TCP can use TCP as almost like a file that you write to and you read from. And you can write lots of data or just a single byte. And you can read a single byte or read 2 gigabytes. Okay? So it's a very flexible device. So TCP here receives bytes and transmits bytes up and down to the application layer, but it uses IP to do its job. So it probably, bunches together a number of bytes in a reasonable size and then transmits that using IP. Needs to keep track of whether this packet has arrived or not. If it doesn't arrive, it has to do retransmissions and so forth. So TCP is a complicated thing. Okay. However, some services up here does not need all that reliability, or rather, it's not willing to pay for the reliability. So UDP comes into play, and UDP is essentially just a wrapper around IP. So it does not refine IP one bit almost. So we can think of UDP as IP. So it's essentially sending packets without any guarantees. But it's quick and it's cheap in the sense that it's not using a lot of network resources to do its job. So both of them are useful. Questions? Okay, so then who decides about these protocols? Because we said that these are evolving organically, but I mean, there are different companies and they need to be interoperable, right? So if I buy a router from D-Link or from Netgear or from Cisco, obviously I would like them to have the same functionality. Okay, so all these companies and governments and so forth, they need to agree upon what the protocol rules are, right? And so long as when there is a new version of a protocol, this needs to be discussed and negotiated and so forth, right? So how is this done? In different collaborative arenas, I would say. And so there are different standardization bodies, and there are more than these, but these are maybe the main ones. So, for instance, there is a body called ITU, which happens to be actually a part of the United Nations. Right? So it's a UN thing. And its areas in telecom. And it has a number of standards that it does. And typically the standard has two names, one which is the technical name and one which is the brand name. It's almost like chemical components. They have a brand name and then they have a chemical formula, right? More technical name. So G.992 is ADSL. Okay, so most people know what ADSL is. Nobody knows what, or I didn't know that this was also G.992. So these are the same thing. MPEG-4, we know, it's also called H.264. Okay, there is a body called IEEE, Institute of Electronic and Electrical Engineers, I believe. And they deal with communications basically. So they're responsible for Ethernet and Wi-Fi, for instance, these standards. We have the Internet Engineering Task Force, which is a bunch of nerds, I think. No, actually, in the beginning it was, but now it's more professional, I think. I mean, nerds did a professional job, don't get me wrong, but it was more a volunteer thing in the beginning. Now it's more structured. And what they do is they put out the HTTP protocol, for instance, and they do that by sending out a document which is called RFC, which stands for Request for Comments. Okay, and then it has a numbering. And in this request for comments, one can understand that this is something that could evolve, right? So people look at this document and say, no, that would never work. We can do it in this way instead. Or here's a more efficient way to do that. And then these gets updated. And maybe there will be in 1.2 here and so forth. Right? You don't want to do that on a daily basis, but every now and then you want to fix something. Yes?
Similar to like an open source, right?
These things, yeah, more or less, right? But then there is a lot of commercial interest in this now, right? So this is not, and that's in all of these. So it's not a political free process striving for the ultimate perfect technology. No. There are some people trying to do that, but there is also people say, okay, I have a patent for this. I want to push that into in the standard so I can make money. Or I don't want to do this because then I will let my competitors have an advantage. So these are complicated political, commercial processes. Okay, and then we have the W3C, which is responsible for HTML, so more like the semantics of the web. And 3GPP, which is responsible for all the mobile phone systems like 2G, 3G, 4G, and 5G. Okay, and all of these are then somehow obviously connected, right? But it's good to know that things are done not always in the interest of having the superior technology to win. That's also a good thing to do. So our roles as engineers is of course to push for this because we want to do things efficiently, right? To provide value with the minimum amount of resources. But it's not always possible, unfortunately. Okay. Now, internet names and addresses. And we touched on that earlier. So what is an internet name? It's something which is unique and easy to remember for people, and it's independent of physical location. So a host has a internet name consisting of two parts, a host and a domain name. So www.chalmers.sc has two parts to it. First, it identifies a node within a domain. Okay. So this is a particular computer, right? Or, and I'm simplifying things, it could be several computers actually. But anyway, so let's think of it as being a host which is running in a certain domain. So there is a hierarchy here. Chalmers.sc might have several hosts, for instance. DNS is used to translate this into an internet address, which is more useful for the IP layer. The IP layer doesn't understand this. So the IP layer needs an IP address, and the IP address uniquely identifies a network interface card. Okay. So in a computer, there is this network interface card, or NIC, right? So an IP address points to this. Okay. So note that the arrow goes this way. So an IP address here. So another IP address, IP prime, might also point to this network interface card. Right? However, it never points to two different network interface cards. Right? So it can never point to this one, right? But with an IP address, I know which NIC I'm looking at. If I know the NIC, I don't know the IP address. It could be 1, it could be 0, it could be 1, or it could be multiple. Okay. But anyways, we're interested in finding the NIC. So the IP address is very nice because it tells me exactly what NIC on the internet I'm looking for. And there is only one with one IP address in the ideal world. Obviously, there are mistakes, and sometimes there are duplicates of IP addresses. And the protocols needs to be able to handle that. But let's think for the moment that things are ideal here. So questions? No? Okay. So routing decisions are based on the destination IP address. So when a packet goes through the network, the routers are looking at the IP address to figure out where to send it. And to do that efficiently, the IP addresses have a hierarchy to it. So for instance, at the router, one first inspects the 120, or one inspects the address from left to right. So then if one looks at here, and then one can see, okay, I know that all 129 IP packets should go out this link. Then I don't care about what's going after here. So I can scan this, and I can send a bunch of packets going to different IP addresses, but they all have the common 129. All of them are going out the same line. Okay? So it's a hierarchical address here that helps routing. Otherwise, the routing table would have to have an entry for all possible IP addresses. And that's not suitable. Okay, the IP address here, these are octal numbers, decimal numbers from 0 to 256. So these are 8-bit numbers. So they're 8-bit, 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 32 bits in total. And this is for IP version 4. IP version 6 is a different format. But let's talk IPv4 here. Questions? Okay. So a network interface card here has an IP address that points to it, but it also has a physical address which is valid for the local network it's connected to. Okay. So a NIC, network interface card here, has a physical address also. So if one has a LAN, a local area network, or some other type of network, there are typically physical address to all the physical attachments or network interface cards which are connected to that network, either physically or logically to that network. So the network itself uses physical address to transfer packets over that network, possibly to a host which is on that network or to a gateway to get to the next network. Okay. IP addresses need therefore to be resolved to physical addresses as they are translated, as they go over the network. Okay, and one typical such physical address is an Ethernet address. So an Ethernet card has a 48-bit address. Each Ethernet card, this network interface card, has a globally unique medium access or physical address. These are the same thing. The MAC address and the physical address is the same thing. Okay? So globally unique means that every card which is manufactured, at manufacturing, it gets a serial number, which is its MAC address, and that should not change, in theory. In practice, one can reprogram the MAC addresses for network interface cards. But let's not talk about practice here. Let's talk about what it should be. Or maybe it should be like that. But anyways, let's consider that as something which is burned into the ROM, which is on the network interface card. It will never change. Okay. Actually, there's a hierarchy to this where the first bits here, the first 24 bits, identifies the manufacturer. So this happens to be the one of my in the laptop here. It has this MAC address, 24A2E1 E6 B4 C4. We see here that these are hex numbers. So A here is 10 and E is what? 14, right? F is 15. So each hex number has 4 bits. So here we have 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8 bits. 6 bytes, 48 bits. Okay, and the first, let's see now, 8 times 3, 24 bits, identified this as an Apple network interface card. Okay, so how are the interconnection between IP addresses and physical address? How does that work? Let's go through an example here to try to illustrate the point. So here we have a very simple network consisting of 2 nodes connected to one network and 1 node connected to the other network. We have a router in between that connects this network, which is an Ethernet network, with this network, which is a super simple network. It's a point-to-point network consisting of just one single host and a router. So the simplest we can think of. Now, IP addresses had 2 parts of it, one which identifies the network and one which identifies the host on that network. So it has 32 bits, but to save space on the slide, we just take 2 decimal numbers here. And the first one identifies which network we're on, and the second one which computer it is, which host. So the server here has a IP address which is 11. It also, and 1 because it's on network 1, and 1 because it's the first host on that network. The workstation has 1, 2, and the router has a network interface card which is pointing into this network, and it has an IP address 1 and 3. So we have 3 nodes attached to network number 1. Okay, all of these nodes also have physical addresses, and it happens to be in Ethernet, so they have Ethernet addresses. The server has S, the router R, the workstation W. And there is a one-to-one correspondence in this simple case between the physical address and the IP address. So the server has IP address in green here, 11, and the physical address S. And the workstation 12 W, the router 13 R. Okay, so this is for network number 1. Network number 2 is so simple that there is no physical addresses needed because it uses this point-to-point protocol. And the point-to-point protocol is essentially a network where we have 2 nodes and 1 connection between them. So there is no need for addressing because there is, if I want to transmit something, it goes to the other end. So there is no need to address, right? So it's very, very simple protocol. So there is no physical addresses in that. Okay. Now, how is encapsulation working here? If we have an IP packet here, we have an IP header and an IP payload. This needs to be transmitted. And the IP layer uses the network interface layer below it. So if we have Ethernet, for instance, below us, if I'm the IP packet, IP layer, I push my IP packet down to the layer below it, and the layer below it puts on its headers. In this case, an Ethernet header, and then there is an Ethernet trailer also, which is known as an FCS, which stands for Frame Control Sequence, I think. Checksum, sorry. That's here. Checksum. And it's for error detection. So the question before, it's these are served for error detection. And it's placed at the end here because this is the first bit which is transmitted, and then one can pipeline everything at the receiver. So it's for implementation purposes. Okay, so in the Ethernet header here, there is a source and destination addresses. And since Ethernet only understands Ethernet addresses, these are the physical addresses, the MAC addresses. The IP header has the IP addresses. But Ethernet does not look at the IP headers. It doesn't look into this at all. So it only uses what it gets from above, which is an IP packet, and it also gets from the IP layer the Ethernet addresses to use. Okay. Now, at the receiving end, of course, the receiving Ethernet entity needs to figure out what to do with this. And in the Ethernet header, there is a field that tells us that this is an IP packet. Then the receiver Ethernet card knows that the payload is an IP packet and can push it up to the IP layer. Because it could be some other packet also, and then it should go through some other hole in the roof. Right? Okay. So the Ethernet header contains the physical addresses and a field that says that this is an IP packet. Okay. Questions? No. So this is an example of this encapsulation process we talked about earlier. So let's see if we want to send an IP packet from the workstation to the server. What's going on? Well, in the workstation, there is a protocol stack. And it consists of many things, but for what's relevant here now is the IP layer and the Ethernet layer. The IP layer needs to transmit, it's been told to transmit a packet from itself, that is 1.2 from the workstation, to the destination 1.1, which is the server. So the IP layer has here, in its header, has this information. These are the IP addresses and payload. So this is the entire IP packet now. And then it's what the IP layer then does is that it inspects the destination address and figures out, okay, so it's on network 1, so it's on my own network. So I can send it directly. I can send it to wherever it needs to go over the Ethernet, because the service is connected to the Ethernet. So it says here that, oh, okay, 1.1, it's actually on my own network and has physical address S, MAC address S. So then the IP packet is encapsulated into an Ethernet layer here. And so the IP protocol here tells the Ethernet protocol, okay, here's a packet and please send it to S. Okay. Now the Ethernet layer knows that its own physical address is W, so it just appends it to this one. Okay. So now the IP, there was some upper layer and then became an IP layer and then a packet, and now it became an Ethernet frame or Ethernet packet. And now it needs to be transmitted. So then it's sent out on the wire and then picked up by the network interface card at the server. It goes like this. Okay. So now at the server, the Ethernet layer here has an Ethernet frame, which has the source and, sorry, the destination and the source. So it sees here, it's the source and destination. Okay, and it knows it's S. Okay, so this packet is for me. So what is it? Well, then it looks in this. Oh, it's an IP packet. Okay, then I'll tell my IP layer that I got an IP packet and delivers it up to the IP layer. Yeah, so it's like this. So now the IP layer at this machine has talked to the IP layer at that machine through its Ethernet connection, through encapsulation and use of physical address. Questions on this? Okay. A slightly more complicated thing here then, from the server to the PC, we see now that the data needs to go over two networks, right? The Ethernet network and the point-to-point network. So here's the first example of of an internet, simplest internet you can think of possibly, right? So what's going on here? There is an IP packet here from 1.1 and it should go to 2.2. So it's here. It's pushed down to the Ethernet layer, and here the IP layer here knows it goes to 2.2. Okay, so it knows that it's going to the network 2. The IP layer knows it's on network 1. Okay, so it's not to our local network. So what to do? I send it to the router, and the router will figure out what to do with it. Okay, so what it does here is that it sends the Ethernet frame with the source and destination, where the source is the server and the destination is the router, and the router's physical address here. And then it's framed, sent, and then this transmission is then picked up by the network interface card, which is pointing towards the Ethernet here at the router. Okay, the router has then received, its Ethernet layer has then received the Ethernet frame here. So it looks at the destination and says, okay, it's for me. And then it looks into the header and says, okay, it's an IP packet. Okay, then I send it up to my IP layer. Sends it up. Okay. Now the IP layer looks at this. Okay, so this is a packet to 2.2. Okay, but that's not me because I'm 1.3. So it should go somewhere else. So I'll just push it, and where should it go? Well, it should go to network number 2, and I know that's this output port. Okay, so it pushes it over to that side and then pushes it down to the network interface layer, which is on this side now. Okay, and then it gets transmitted over here. One puts on a small header here. PPP has a small header, and it gets transmitted over here, gets picked up by the network interface card. Here there's not so much addressing to inspect, because if it gets a packet, it's for itself, right? And then it just pushes this up to the IP layer like this. Okay? Questions? Okay. The first time one sees this is maybe a little bit complicated, right? So you might want to look into this. Yes?
What's in the PPP layer or the header?
I don't know. Hello, maybe? Is it something do you need physically in order to wake up the receiver, and maybe some small control information. I don't know the details of this actually, but it's very, very small. Okay. Yes. We have more? No, okay, yeah, okay. So here, if one wants to have, here's the physical layout of the network, but from a protocol layer point of view, we have a protocol stack at the web server, and here a protocol stack at the web browser, or at the PC. which is running a web browser, and it's actually requested a page from the web server. So if that is the case, we know that the application layer that transmits web pages is called HTTP. So this HTTP entity wants to talk with this HTTP entity, right? But it cannot do that directly because they are on two different networks. So therefore, there is a router in between, and the router also have a protocol stack here. However, we see that the protocol stack at the router does not include the transport or the application layer entities because it doesn't need it. Okay. So data that goes from here to here goes like this. It gets encapsulated along the way, and then it's on the Ethernet, and then it runs over the Ethernet and ends up at the network interface card at the router, which is attached to the Ethernet. It picks up here, and then it comes to the IP layer. And the IP layer realizes, okay, it's not for me, but it's for something which is on this end. And then it gets encapsulated and then transmitted over here, and then strip off the headers and then reach here. Right? So there is no need for a transport layer here, because the transport layer here is an end-to-end protocol, while the IP is a sort of like a link-to-link protocol. It goes like this. Okay. But of course, they need to be coordinated in order to figure out the route of the packet. Okay? Right. So from an abstract point of view, these Ethernet and point-to-point protocols just provides some connectivity over a network for the IP layer. So the IP layer here uses this network here and that network here. So that's the abstraction for that. So IP provides unreliable packet transmission over these. Now, IP here hides what's going on here for TCP like this. It just provides, instead of saying that it's two networks here, TCP just sees it's one network, namely a special instance of the internet. Right? What does HTTP see? Well, it sees here, TCP here sees unreliable transmission over this network because it uses IP. IP does not guarantee anything. But it can refine the service for HTTP by adding reliability to it. And therefore, for HTTP, it looks just like a straight line. No problems, no errors ever. Right? And therefore, we can draw it like this. Nice and clean, right? But messy down here. So this is the power of the abstraction here. Okay. I think what we do now, any questions right now? No? Okay, so let's take a break and maybe reconvene 3 minutes after the hour and get you 15 minutes.